Hello and welcome to Empowered Learning. This particular video will be about composite functions, which are also known as composition functions. Our objectives here are to form a composite function and determine its domain, evaluate a composite function, and then look at a composite function and decompose it into what we call its outside function and its inside function. So the first thing we want to do is properly define what a composite function is. And so simply put, a composite function is a function that is made up of two other functions where one of those functions is literally stuffed inside of the other function. Okay, and hence we call that a composition. So given any two functions f and g, the composition of f and g, also said as the composition of f and g, denoted by the f open circle g, is defined as follows. And so you'll see how we have the inside function g of x right here. That's actually stuffed into the outside function f of x. So we look at the g of x as the inside function, and of course the f as the outside function. Okay. And so, of course, the domain of f and g is a set of all numbers x in the domain of g, such that in turn g of x is in the domain of f. So in other words, we have to first satisfy the domain of the function g of x, and then all those corresponding y values for g of x have to be in the domain of f of x. And so we're going to learn how to deal with that. And so down here again, I just mentioned that the composition of f and g is formed by stuffing and g of x, which is known as the inside function, into the function f, which is known as the outside function. Okay. So we'll go ahead and move on here to some examples. So our very first example says, given that we have f of x 3x plus 1, g of x is x squared minus 2x minus 6, and h of x is x cubed, we want to find the following. And so for the first example, you'll see that what we've done is we've translated what the composition of f and g evaluated at -1 means. It means that first we need to figure out what g of -1 is, and then we plug in what g of -1 is into f. So as you see, as our first step, we know that our g of x function is this, so we just plug in -1 into it. We see that once we evaluate all that, we end up getting a -3. And so from that, we are basically taking that -3 and plugging that in for g of -1 right there, and hence why we have that. And so now f of -3, we just plug in -3 into this function here. And when we do that, 3 times -3 is a -9, plus 1 ends up being a -8. And so we know that f of g of -1 is -8. So with the next example, we can go ahead and work on it. So let's look at what our function g is. So of course we know this means g of f of 5. So the first thing we have to do is figure out what f of 5 is. And so of course our f of x function is 3x plus 1. So we just plug in 5 into there, and we see that we get 16. Okay. So from that, we know that g of f of 5 is going to be g of 16. And for g, we see that we have our quadratic function here. So that will be 16 squared minus 2 times 16 minus 6. Okay? And so all we need to do from this point is go ahead and work out what this is going to be. So if we look at this, 16 squared will end up being 256. And of course, 2 times 16 is 32 minus 6. And when we work all that out, we end up getting 218 as an answer. So thus, the answer to this question will be 218. Moving on to our next example, we have h of g of 3. So this would look like that. And so the first thing that we would need to do is figure out what g of 3 is. And so we know g is going to be the function, we'll just rewrite it right here. It's the function x squared minus 2x minus 6. So we'll plug in 3 into there. Of course, this is 9 minus 6 minus 6, which would be 9 minus 12, which would be a negative 3. So now we know that g of 3 is a negative 3. So h of g of 3 will be h of negative 3. And of course, we have to remember what h is, so we'll go back up here right quick. So our h was x cubed. I'll just rewrite that here. So here we just have negative 3 cubed, and that ends up being a negative 27. And so this is how we can take composite functions at a particular x value and evaluate them. In all these cases, we're basically working on the inside function first to get that particular y value's answer, and then we plug that y value into the x value of the outside function. All right, so next what we're going to do is look at this a little different, and instead of having an algebraic version of the function, what we're going to do is have a table version of the function at some points, and then from that figure out how to evaluate it, and then we're going to do the same thing from a graph. So if we start off, we see that we have f of g of 1, and so f of g of 1 is the same as writing it like this. So the first thing that we have to do is find out what g of 1 is. So here, when x is 1, we need to find out what g is. So we see these two things intersect when that is 0. So that's why we have 0 in place of this. So now once that's done, what we need to do is look at this and now say, all right, well, let's find when x is 0, what f is. So when x is 0, what is f? And we see the place where these two intersect would be negative 1. So that's why our answer here is negative 1. Okay. So for our next example, we know that this is f of g of negative 1 in this case. And so now what we need to do is look at, first of all, when x is negative 1, what is g going to be? So we see the intersection in between that is going to be 0. Okay. And so of course, just like last time, we know that f of 0 is still negative 1, because when x is 0, f is negative 1. So now we'll move on to our next example here. Don't want to erase all of that, but I'll go ahead and replace that right quick. 0. So now we know that this translates to being g of f of negative 1. And so what we want to do now is find out what f of negative 1 is. So see where these two intersect. See, that will be at negative 3. And so now g of negative 3, go ahead and get rid of this first thing. So when x is negative 3, which is right here, g of negative 3 will be 8. course, for our example D here, go ahead and go through that quickly. So here we see that g of f of 0 is the same as g of f of 0 here. And we know that f of 0, from what we saw up here, is just a -1. And we know that g of -1, so when x is -1, what is g? We see that ends up equaling 0. Oh, excuse me. Sorry about that. And so we see how we get 0 right here. For our last example, do you see how we have g of -2? So for this one, we say g of -2. And first, what we want to figure out is when x is -2, what is g going to be? Okay, so here when x is -2, what is g going to be? That's going to be 3. And so now when x is 3, you see that g is 8. All right, so we see how to look at table of points for two different functions and translate or evaluate composition functions from there. So now let's look at the case of, instead of having the table of points, we have a graph. Okay. So in this case, we'll follow the same thing, but instead of looking at a table, we're just going to find out what the corresponding x and y coordinates are. So for the first example here, we know that this is going to be g of f of 1. And so the first thing we have to find out, what is f of 1? So when x is 1, which would be right here, our function f is the black one, it would be this point. That would be a -1 for the y value, because, move this point back here, we know that that point there is the point 1, -1. So when x is 1, y is -1. So we come here and just say that this is g of -1. Okay? And so now from there, we'll move on and say, what is g of -1? So g is the blue graph. So when when x is equal to -1, which we're looking here for the x, corresponding y value would be at this point, which is 1, 2, 3. So g of -1 would be 3. Okay, so let's go ahead and move on to the next example. So here we have g of f of 5. And so now we're going to look for the y value when for the y value for f when x is 5. So we count 1, 2, 3, 4, 5, and then go up on f. You see that we're right here, and that corresponding y value is a 1. And so now we look at the blue graph for g and say, when x is 1, what is the corresponding y value? 1, 2, 3, 4. So we see that g of f of 5 ends up just being 4. Okay. Example C here, if you notice, what we've done is we've written the out what the composition function actually is, instead of putting it in this notation here, because normally we've been putting it in this notation, but we wrote it directly like this so that you can see it in a different way. And so, of course, we need to find out what g of 2 is. So looking here, let's go ahead and erase what we had from last example. So here, when x is 2, we know that g of 2 is 2. And so when x is 2, we look for f now, and we go down, you see that that is -2. So f of g of 2 is negative 2. Similarly, we know that we need to find out first what g of 0 is. So, get rid of this to get a fresh example. Let's just erase. So when x is 0, for g, which is the blue graph, we know that we go up 1, 2, 3, 4, 5. And of course, f of 5, from what we saw over here, we know that that's just going to be 1. Okay. And of course, if we look here, 1, 2, 3, 4, 5, this is the point 5, 1 on its graph. All right, so what we've done up to this point is examples on how to take the composition of two functions and evaluate it for a certain value of x. What we're going to do now is take two functions and form a new function called the composition function, and also find out what the domain of those functions would be. Okay. And so in these examples, we're going to take a function f and a function g. We will form what the composition function f of g of x is, and then we'll turn that around and talk about what g of f of x is and figure out the corresponding domain for each. Okay. So to start off with, we have the function f of x, which is 4 divided by 1 minus 5x, and g of x, which is 1 over x. And we see that right here. What we are asked to do is to form what the composition function of f and g would be, and the composition function of g and f, where in the first one, we know that g is going to be the inside function, whereas second one, f, is the inside function. Now, if you've checked out my video on linear transformations, then you'll probably be familiar with what I'm saying here in the note. If you're not, I encourage you to check out that particular video, as it provides some insight into how to look at the domain of a function when we're trying to, when that function is actually combined from two other functions. And so we're going to use that same concept here. So we know that f of g of x, everywhere where we see x here, we need to replace it with what g of x is. So we literally do that there. And then we know that g of x is 1 over x. And of course, if we multiply this term together and simplify, it looks like this. Now, my note here is that if we're going to find out what the domain of this function is, we need to look at that function in that form right there to determine that. We cannot be misled by continuing the process to simplify what this expression looks like, and then at this point look at what the domain is. Okay. And so the reason for that is because in the raw form we see everything, whereas once we simplify it out, there's some things that we miss. And so in particular, I'm going to go down here and show you what I mean by that. Okay. So the function f of g of x, we know that once you simplify everything, it comes out to be this. And similarly, for g of f of x, the actual expression for the function, when you simplify it, it comes out to be that. However, we are, as soon as we plug in the inside function, it is at that point we look to try to evaluate the domain. Okay. So for the domain of f of g of x, we see that we have two restrictions. And so the first is we know that this entire domain cannot equal 0. So that's what this is saying. Okay. And if we take this, I'm doing it real fancy right here, but at the end of the day, we know that we can't allow this to be 1. Okay. And we know that if we plug in 5 right here for x, 5 divided by 5 is 1. So that's the thing that we can't have. We also know that because this is in the denominator, x is in the denominator of a fraction, it cannot be allowed to be equal to 0 either. So from that, we know that our two restrictions are, if we are going to plug in values of x, we cannot plug in 0 and we cannot plug in 5. Now, to make my point, if we come back up here to what the result of f of g of x is, if you look, the only thing that it alludes to is that I cannot plug in a value of 5. That end result does not allude to the fact that you also cannot plug in 0 at all. And that's the hidden secret. So that's why we have to make sure that we look at the domain in this form so that we can see everything. Okay? All right, so now let's look at the domain of g of f of x. Okay, so we know that g of f of x in its raw form looks like this. And of course, we know that 4 divided by 1 minus 5x can't equal 0, and 1 minus 5x cannot equal 0. Because we know 1 minus 5x is in the denominator of this complex fraction. Okay? And of course, 4 divided by 1 minus 5x is a whole denominator within itself. So looking forward here, we see if we were to try to solve this, we would see that we just get 4 does not equal 0, which we know is no solution. If we solve this by adding 5x to both sides, then we see we have 1 is not equal to 5x. And of course, if we divide both sides by 5, we see that x cannot be equal to 1/5. So we know that out of everything, the only value of x that we can't plug in is 1/5. So in interval notation, this would look this way. Okay. All right. So again, if we would have looked at the function f of g of x and g of f of x in its form, simplified form, then of course we would have thought that the domain of this would just been all real numbers except for 5, and we would have thought here that the domain was all real numbers. But we see that that is incorrect. Okay, and so that is why we have to again look at the raw form of the function, of the new function that we're forming. And what I mean by the raw form, the form right after we plug in what the inside function is into the outside function. All right. So for our next example, we have f of x is square root of x, and g of x is 2 minus 3x. Okay. So if we form f of g of x, where g of x is the inside function, then we stuff this linear function into the square root, and we end up having this. If we do it the other way, where f is the inside function, now we have 2 minus 3 times square root of x. Okay? And so if we look here, for both of these cases, here and here are the raw form of the composition function, and it also is the simplified form. So this is an easier case that we can deal with. So looking here for the domain, we know that whatever is under an even nth root, and in this case a square root is an even nth root, that expression has to be greater than or equal to 0. Okay, so because of that, we have to solve this particular linear inequality for x, and when we do that by adding 3x to both sides here and then dividing by 3, we see that x is less than or equal to 2/3. So we're restricted in plugging in values of x that are 2/3 or lower into that. For the domain of g of f of x, we see that the only restriction that we have is this x under the radical here has to be greater than or equal to 0. So thus, our domain is just values of x that are greater than or equal to 0. All right, so now we're going to do some examples on our own here. So we'll start off with this first one. We want to form what f of g of x is and what g of f of x is, and then find the domain of each. So we'll start off with f of g of x. Everywhere where we see x, we will replace it with g of x. Okay. So here we would say g of x squared minus g of x plus 10. And of course, this would just be 2 minus 7 squared minus 2x minus 7 plus 10. Okay? And if you want, you could go ahead and multiply all that out by foiling and whatnot. I'm not going to do that just because it's not consequential to what it is that we need to do, which is find the domain. Okay? So here and here are places where we look to see, do we have any restrictions on our domain? And since we do not have any case where we're plugging in an x value that will make us divide by 0, or we do not have a case where we have a negative number, we're not plugging in a number that will make us have a negative number under an even nth root, like square root, fourth root, sixth root, so on and so forth. The domain of f of g is just going to be all real numbers. Okay. So now let's look at g of f of x. Let's do some separation here. So now everything's in reverse. So now what we're going to do is take our function f and stuff it into g. So this would be 2 times f of x minus 7. So this would be 2 times here 4x squared minus x plus 10. And that will be a minus 7. And we'll just say that is 8x squared minus 2x plus 12 minus 7. And then that result there will be 8x squared minus 2x plus 5. Okay. Now the raw form of this function is here. And if you notice, we have a quadratic. We still don't have anything that makes us divide by 0 if you plug in an x value. And we don't have any square roots, fourth roots, or anything like that. So again, the domain of g of f of x is going to be all real numbers. Okay. Moving on to our next example. So we have f of g of x. And so everywhere where we see x and f, we're going to replace it with g. And so we know that that's just going to be square root of x. And so we have 2 times square root of x plus 1. Okay. For g of f of x, turn the tables around. And so in doing that, everywhere where we see x in g, we're going to replace it with f. So it look like this, and then we're just literally plugging it in. By the way, if you can already see that g of x is going to be just square root of x, you can skip this step right here and skip this step right here and just go directly to what the result is. Okay. So for the domain of f of g, if you notice here for f of g of x, the only thing that we have under the square root sign is x. So here we have to make sure that x is greater than or equal to 0. So the domain of that is going to be all real numbers such that x is greater than or equal to 0, which in integral notation looks like this. For the domain of g of f of x, we see that we have 2x minus 1 under a square root sign. So therefore we know 2x plus 1 has to be greater than or equal to 0. And solving that, we see that x has to be greater than or equal to negative 1/2. Okay, so here that would look like this in integral notation. Okay. All right, so our next example, we're going to take our two functions here and form functions again. So f of g of x, we're going to write it like this. And so now everywhere where we see g of x, we're going to, everywhere where we see x in f, we're going to stuff g of x into it. So we're going to take this, stuff it in there. Okay? And if we do that, we see that we get this. Now, at this point, this is the raw form of the function. So we have to figure out what our domain is going to be from there. If we go on to continue to figure out just what the expression of the function will end up being, then this would just be 6 times, and then we flip this bottom fraction 1 over 2x plus 1, which ends up looking like this. And of course, we can always write 6 over 1. So this would just end up being 6 times 2x plus 1 here, which is 12x plus 6. Okay. Now to find the domain of this function, we see that here in the raw form, we know that 2x plus 1 is not allowed to equal 0. We also know that the entire denominator is not allowed to be 0 as well. Okay. Over here on the right, if we solve 2x plus 1 not equal to 0, what we're going to end up with is x cannot equal 1/2. Okay. On this side, if we put this over 1, let's see if I can write it in there, and cross multiply, then the result that we're going to get there is just that 1 is not equal to 0, which means we have no solution there. Put another way, there's no value of x that we can plug into 1 over 2x plus 1 to equal 0. Okay. So from that point, we see that the only restriction that we have is that x cannot equal negative 1/2. So here, to write that in interval notation, that would look like this. Okay. So now for g of f of x, here we would write this as g of f of x, and everywhere where we see x in g, we are going to now stuff that into f. So here, to try to get this looking the way I want, I want to erase all of this. And so now we're doing the opposite. So we're going to take f, take that and stuff that into g right there. So this would be 1 over 2 f of x plus 1, which will be 1 over 2 6 over x plus 1. Okay. And of course, we could simplify this a little bit. And we're going to come over here to do that. So this would be 1 over 12 over x plus 1. And so right here, we would use this as the raw form of our function. Okay. And we'll talk about how to simplify this here now, and then we'll get into the domain of it later. So here, what we can do to simplify this, we can multiply both the numerator and denominator by x to get rid of the fraction. So in the numerator, this will just be x. In the denominator, when we multiply, didn't need to move that. When we multiply, we have to distribute to both terms there. So 12 divided by x times x is just 12, and x times 1 is just x. So this is what the simplified form of the function would look like. As far as the domain is concerned, we have two things that we need to consider. Okay. And so the first thing is that we know that the entire domain, 12x plus 1, cannot equal 0. Okay. And we also know that x itself cannot equal 0 because of this part. Okay? So here to say 12 divided by x plus 1 cannot equal 0 is the same thing as saying that 12 divided by x cannot equal 1. And of course we know that 12 divided by a negative 12 would give us a negative 1. So here, we do some cross multiplication. We see that negative x can't equal 12. And from that, x can't equal negative 12 if we multiply both sides of the equation by negative 1. So, our restrictions are these two. And so the domain of g of f of x is going to be all real numbers except for negative 12 and 0. And of course, in interval notation, we would write that as negative infinity to negative 12, union negative 12 to 0, and then from 0 to infinity.